Thank you. Hello, welcome to Advent of Code in F star. I believe this is day 15. A little late getting started here. So let's move things around and we'll get started. All right, here we are. Day 15 is started already. It's another risk level puzzle. Okay, so we're just gonna find the minimum risk level from the upper left to the bottom right. So what's our input like? Our input is big. All right, so we're gonna reuse the matrix loading code that we wrote on a previous day. No. There it is. Okay, so here I did it all fixed sized. So where did I copy that from? Okay, there it is. So we will make a directory for day 15. And Copy the day 9 code. All right. Okay, we need the vector matrix. We don't actually need the neighbor code. We're going to do something a little different. Okay. We need the code to parse the row. Okay, so there's our code from before to parse a row of integers and to parse the whole matrix given its width and read the first line and the width and return the matrix and its size as not as a record but as a type with a single constructor, which is sort of like a record, but it's accessed differently. Okay. And then copy that. Okay. So what we want to do instead of finding local minima is find the minimum path. And we'll do something with it. Okay. So the easiest way to solve this is with dynamic programming. So, if we think of solving if we look at the bottom right-hand corner, there's only two ways to get there. We can come in from the side or from the top. And so the minimum cost path to X is going to be the minimum cost path to A plus this arrow. I'll make that an arrow. So cost of getting to X equals the min of cost of getting to A plus A to X, and the cost of B and the cost of getting from B to X. All right. So, well, what's the cost of getting to A or B? It's recursively, you can come in from the top down or from left right. So let's see. Is this a true fact? I mean, it's basically going to be Dijkstra's algorithm if we did it in full generality. So maybe, I guess that would be true if we could only go. Yeah, so that's not going to work because we can, in theory, backtrack. The example does not do that. So I guess we have to do. Well, let's think about this. Yeah, it's not really for dynamic programming. That would be if we wanted to count the number of paths. So it's really more like a search. And so we could use, how big is our input again? It's pretty big, but not huge. Yeah, let's implement Dijkstra's. There are other ways we could do it. Okay. So to do this, we need a priority queue though, and that's going to be tricky because I don't have a priority queue in F star. So it's going to be less than ideal unless we write a heap. I don't know, should we write a heap? How close to optimal do we have to be to actually get done in a reasonable amount of time? So the problem is looking through everything, or even everything with a finite value, is going to be a really big search. So I think, all right, this may be the wrong way to go, but let's build a heap. All right, so this is wrong. All right, so a heap, and what we're going to do is we're going to give the heap, so what I'm going to do is I'm going to look at this half converted red black tree. So this is one of the examples, and I was modifying it to take other values as keys and be able to store a value. The example there only has nats, and it turns out there's a good reason that they did it that way. So what they did is say the height of the tree node is one of the parameters of the type. So I'm going to try doing that. All right. So if it's a leaf, um, it doesn't have any parameters. Otherwise, a node has a heap, has a height, and to keep it balanced, what we want to do is, am I really doing this? Can we implement Dijkstra in some other way or use something besides a heap? We could use a big vector and do radix sorting. We could sort in between every modification. I should have done my pre-work here. I was thinking that maybe I should put a heap together. All right, we'll do it so we can implement Dijkstra's. Okay, so a node is a non-leaf node has a left. That doesn't look right. Oh, okay. Their height is a little bit different than what I want to do. All right, what I kind of want to do is have the requirement that either the left or the right has heap minus height -1, and the other one can have a smaller value. Because what we want for the heap property is that it's a nearly complete binary tree. So, it should look like it should look something like this, right? So it's allowed that y is 1 shorter than, oh, okay. So it's always the right node that is going to be less deep if we fill in the tree sort of from left to right in the bottom row like a conventional heap. So a lot of heap implementations use a mutable array and just swap things around, and that does not seem like it's going to work very well. So this is going to be a heap of height h -1. All right, except we actually need to put values in here. So what do we care about? We care about its position. Okay, so care about its distance. Oh, no, we'll do this here. I'm thinking about how to express the heap property that the two children are both left less than the parent. We may not want to encode that here because we might want to temporarily violate it while we're moving things around. So this will just encode the structural property of being a complete binary tree without the ordering. Okay. So we're going to do a key, which is a natural number, and a value, which is going to be a pair. We better parameterize that. Because we might want to put a refined type in there. Okay, so we're going to have to do something a little funky here, which is each right is a natural number, and it is either -1 or -2. Right, so if this has height 2, this has height 0, and this has height 1, or something like that. This might actually be a 1 because it's got 2 leaves that are 0. All right. So the right is a heap node of height HR. All right, let's see if that flies. All right, complain that couldn't resolve the implicit type. This is going to be a problem that this parameter is not constant. So maybe we can't do this. Oh, node. Oh, okay. Why did we get away with it above and we didn't get away with it below? What's different here? Okay, I see. V0. All right, so this will only work if this is a height that is greater than 0. All right, accepted that. Okay, so we got a leaf, which is heap node of height 0 of some type, which we hope is just implicit argument. Otherwise, you've got a height and the type of the value stored in the tree. We have a leaf, a left subtree, a key value, a right subtree, the height of the right subtree itself, and it gives us the heap node. So a lot of parameters to match. Okay. So what so let's see. Okay, there's the empty heap. So let's do let's insert all right. So we insert into a heap by looking at the root value. And if we're greater than all right, we're building a min heap. So if we're less than the root, we replace the root and recurse down one of the branches, the left one or the right one, depending on whether they're even. All right. So I don't know whether that's going to work to be a implicit algorithm. So root is a heap node of that type. And so we need a key value fee. Oh, this is the wrong syntax. Okay, so we matched with the root. So if it's a leaf, then we add a new intermediate node in its place. So we're writing what is the replacement for the tree or the subtree when we insert. So if it's a leaf, then have a new node, and hopefully the first arguments are implicit. I'm wondering, can we tell when we have to increase the height of the whole tree? It should be the case that since complete binary tree, that'll only happen when the heights are equal. All right. I wish I remembered more about this data structure. I haven't had to write one in a while because I've just used the heap library. All right, so it's going to be node with the left is a leaf, key value 0, and another leaf. Yeah, failed to resolve implicit argument. Okay, this is a problem. Can we describe the return type in terms of what we've been given here? Okay, so new height. So what I said, and what I hope is true, is leaf, then the new height is going to be 1. And if it's a node with, you don't care what the left. I really wish I remembered whether the pattern matching included implicit arguments or not. I guess we'll find out. Key value, right. Okay. Too many pattern algorithm arguments. Okay, so we know the left has height h minus 1, so right, the height of the left is h minus 1, which had better be a natural number, because we can only reach this case if it can only be a node if the implicit height argument is greater than 0. All right, so if h left equals h right, then the new height of the root is going to be hl plus 1. Otherwise, the right has room, so it's going to stay the same. Okay. So left, node key, node value, height of the right, right. Okay, so what, sorry, I wanted to do the return value here, which is, it's going to be a heap node that stores V's that is has the new height described by the algorithm above. Okay. I'm just going to double check that there's not a heap in the examples. Oh, that's right. This is the problem. Is Heap is used for the memory storage, which is the other meaning of Heap, not Heap as in the data structure. What have we got in data structures? We've got a red black tree, which we could use. We've got a binary search tree. I don't know what a lens is. We got a vector. All right. Nope, no help there. All right, so let me comment my code so I remember what's going on here. If the tree is balanced, then do we have to keep track of whether... All right, I'm not too proud to look up Wikipedia. Does it have pseudocode for implementing as a tree? It does not. Heaps are usually implemented as an array. What if we don't? Interesting. Okay. Yeah, that's not useful. All right, let's do that. Okay, so instead of keeping track, I think we still need to keep track of... Hello. I'm getting myself in trouble here today. Instead of spending the time actually solving the problem, I'm building the data structure that I don't have an existing S star implementation for in F star. Okay. Okay, so what we need is... All right, so this is a lot of state to keep track of. I'm going to break this into multiple lines. Okay, so for the left, we need a left number children. That's a natural number. Okay, and for the right, we need both its height and the right number of children. No, okay, and so this results in, I guess it's not number of children, it's number of nodes. Right, number of nodes. Well, we're counting the number of non-leaf nodes. All right, so this we can calculate. It's the left number of nodes plus the right number of nodes plus 1. Has to think a long time about that. All right. Good. All right, so let's fix this. So this is left number of nodes. Is this still enough to calculate the new height? Or is the height, should we generalize the height? Do we even need it at all? I guess let me look at the Stack Overflow answer again. This only has one vote. None of these have a lot of votes. Yeah, I don't like this answer. It is correct. It uses less storage, but it seems just harder to do. It's very clever, and F star is not good at clever. Okay, so this is gonna have one. It's gonna be 5, 3, 1. All right. So I think we don't need the height. And that'll simplify things a lot. Unless it gives us crap for not being able to prove that the data structure is finite. Let's give that a try. All right. Let's see if we can get through that. That'll make things a lot simpler. Okay. All right. So if we insert, okay, so if you've got a number of nodes in the tree is our argument instead of the height. So if you've got something with that many nodes and we add 1, we should get one more node in the tree. All right. So that is a node with its left number nodes is 0. Key value right number nodes is 0. Okay. So left. Okay, so left number nodes, left. The node the node key, the node value, the right number of nodes, and the right value. Okay. So if if the key we're trying to insert is less than this key, then replace the current node. I'll write that in a second. Otherwise, we're going to recursively insert into one of the other nodes. So if left NN is does this idea actually work? Okay, so in here we'd say, okay, go to, so if they're equal, we're going to go to the left, and if they're greater than, we're going to go to the right. And so we should encode that it in this type. So the right number of neighbors is always less than or equal to the left number of nodes. Right, that's what we mean by being a complete binary tree. Okay, so if it's right, that's not how it normally works. But this should result in balance. It'll just be in the wrong order compared to the binary tree, but it still will be balanced. So we'll start out. Okay, we'll start out with 0, then we'll go 1 0. I'll go 1 1. Oops. We'll go 2 1, so it'll look like X A Y B. Okay, and then when it's 2 and 2, we will go and add there. Dang it. Okay, and then the next one will go there, and the next one will go there. All right, so we'll fill it in. It just won't be the same order as the array-based implementation. Okay, so we'll just do less than or equal to. So the tree as a whole and each subtree will be balanced. And if there's a overage of 1, it'll be on the left. Okay, so this looks like a node. The left side goes up by 1. Here's our recursive call. We leave the node values alone. We leave the right side alone. Oops. Okay. So our recursive call is inserts on to left the same key in value. All right, let's see if just that case works. Oops. What happened? Parser. Oh. All right. So it type checked. It agreed, yes, you provided a heap node of size nn plus 1. All right. So insert on the right. So we leave the left number of nodes alone, the left alone, this node's key and value alone, and the number of nodes on the right goes up by 1. And so insert right key value. All right. And so I don't see a good way off the top of my head of not duplicating this logic in this case, which is kind of unfortunate. Okay, so we're going to replace the current node and then push the old key and value further down the tree. So it's the same logic. So okay, so instead of the old value, we have the new one, and the old one is what goes down the tree recursively. So we could probably encapsulate this. Okay. Could probably encapsulate this in the appropriately written function, but let's see if that type checks. It does. Amazing. All right, is this a waste of time? Because the problem is that for this to work, we're going to have to go in and update some random value to some random key to a new value. We're going to have to find the XY coordinate in the heap and decrease it. So what can we do about that? Shoot. So we're shaping up to do perfectly lovely heap implementation, but it doesn't have all the properties we need. So to implement Dijkstra's algorithm and find the shortest path, we're going to find the neighbors of the new node we relaxed and possibly decrease their priority. Well, this is frustrating because I know the algorithm. I've implemented the algorithm before, but not in F star, and I've only done it in a very imperative sort of fashion. So what does it look like when it's done functionally instead? I don't know. So, what could we do? We could switch to implementing the heap as an array, and it could keep track of for every XY pair, where is it in the heap? And that's what you'd typically do in a priority queue. Is there a priority queue in the examples? No. Oh, there's lots of prints and prims. All right, that's not helpful. So we could go back to our idea of just keeping a sorted list as our priority queue and pay the cost of resorting it each time and the cost of linear search to find the neighbors. Or we could allow each node to be in the heap multiple times. So we never do a update. We'd only insert and remove. And so that would mean our heap is bigger because an object might be in multiple times, but it should only be in a constant multiple. So we just have to remember that we had relaxed it. Okay. Not saying this is a great plan, but it's the plan I got. All right, so let me make a note of that. Okay. Okay, I can live with that. Okay, so we don't need update in place. We do need a pop. So this returns a heap node V that has one less node and a key and a value. It returns a triple. We could use a record or something, but I think this will be okay. Maybe we'll regret it. Okay, so the easy part is finding which one we're going to pop. I'm going to call this pop min. It's it's the one that's passed in. So okay, so we can only pop if the heap has size greater than 0. I wonder if this is going to cause us problems later, but all right. So it's got to be a node. Okay. So which side do we move up? So if sizes are equal, move the... okay, we got to compare the key and maybe rebalance. So that's what sucks here. Okay. Because tree rebalancing is a pain. Okay. So we'll probably write this in terms of something else. Okay. In fact, I think what we're going to do is we're actually going to pattern match these. So if, all right, so if the simplest case is we've got exactly one node in the tree, right? So we return leaf, key, and value. Okay. So if the right side is the only other possibility, so if it's got two nodes, then it has to be that the left node, the other node is on the left, so left. Okay, two cases. Those are the simpler ones. Okay, so to figure out which one it is, we actually need to open those nodes up. So we're going to do a pattern match within our pattern. So let me leave those blank for now. Left key. Okay, so that's a very complicated pattern match. So if left key is less than or equal to, left key is, all right, so what is this going to look like when we rebalance? So here's our root. Okay. So we need to rotate. All right, so if we if they're equal numbers of nodes, then we need to take if they're equal numbers, okay, let's write these out. All right, so case one, min is R, and R has the number of nodes are equal, then just take R as the new root. Is that true? No, because we have to compare. But that's just it's the array-based implementation. I see why everybody does this in an array, and unfortunately, that's just not a good way to do it in F star either. We'd be having, I think, bigger problems. So the B tree example did the rebalancing with a lot of oh wait, no, this is a heap. So we shouldn't have to do we could swap things around as needed. All right. So we can think of this case as take r's value and push the whole down the right. Okay, so if the min is L and NL equals NR, take no, that won't work. Trying to talk myself into it being easier, but we need to maintain the heap property at every level. So we can always replace L by a smaller value than it had before, but we can't replace it by a larger value. Okay, so okay, but this case still works, right? Move r's value into x, and then r needs a value from one of its children, so we're going to recurse. Okay. So if NL is bigger than NR, so then okay, this was a mistake. Unfortunately, it's still not coming up with a better idea. So one of the things I'm worried about is if we do the heap as an array, then we have to do a lot of splitting it up and joining it back together to do it in a functional way. So would we actually have to go whole hog and reason about it in a stateful way? All right. All right. Let me try another Google search for. Huh. Interesting. I don't really want heap sort. All right, we're going to start over and build a leftist heap instead. I see. All right. I'm going to save my work here. And we're going to start over. Could we, okay, instead of doing that, could we use the same idea and do a merge? Could we do a merge on the heap structure as it's defined? Or would that end up touching every, I'm worried that would end up touching every node. So it'd be a very inefficient pop. Like I said, I'm gonna solve this, and I think some of the work we did can be. Oh, part one. Okay, so a leftist heap I'm going to copy this URL in. All right, so a leftist heap has the number of nodes between x and a null in its subtree, where the min distance to a descendant with 0 or 1 children. All right, let's do it in terms of null rather than k. I don't know that we need an argument for that. We'll find out. All right, so oops. Okay, so X. I realize you may have trouble seeing this. I'm gonna add it here. Null path length. Having it be -1 is just a pain. All right, we can accommodate. Okay. All right. We're gonna simplify our lives by introducing a type. So, what do we call it? We want to call it the type of numbers that are greater than equal to -1. So I can't think of a good name for this. Tempted to just call it myInt, or let's call it int1. Okay. so the right neighbor, okay, the NPL right is a int1, and it is always less than or equal to the one on the left. Less than or equal to. All right. And this results in a heap node whose NPL is 1 plus min of NPL left, NPL right. Oh, NPL. Did I get that order right? Left is greater than or equal to right. Okay. Oops. Arrow. Oh. Hey. Why does heap node v have -1 have type int? Oh, I think we need to do that. All right, and let's write singleton heap key and value v. So that is a node with 0, null, key value 0, null. Oops. Okay, I couldn't prove that was correct. Oh no, these have to be both -1s. So this should be a heap node v0. Okay, good. All right, so the fundamental is merge to leftist heaps. So I have to have the same type. but they can have different, okay. Call them A and B. Oh, this is not a natural number, it's an int1. All right, so the type of this, can we write that type? All right. The root with the smaller value as the new root. All right, pseudocode may be a little more helpful here. I think I can puzzle this out. Okay. All right, so we need to extract, oops, B is a heap node. All right, so the special cases are if one or the other is a null, then we just return the other one. I'm a little worried that we may not be able to write a return type. Okay. So we know these are both. Okay. So what did it say here? Put the root with the smaller value is the new root. Hang its left subtree on the left. Merge its right subtree and the other tree. But before returning, update the MTL and swap to maintain the property. Okay, so the new right is going to be the merge of okay, we're going to merge I think we may have to use a dependent pair to write the return value. I'm not sure we can predict in advance from just the information we have now what the heap value is going to be. So it's going to be a dependent pair so it's going to be the NPL which is an int1 and it's going to be a tree that's a heap node v of that size. Okay, so this has to be the dependent pair. How do we rate dependent pairs? It's a funny syntax. It's going to be NPLA and A. Otherwise, it's going to be NPL B and B. Okay. So okay, so we're going to merge that heap. So we're going to merge. Okay, we're going to take the minimum. Yuck. Okay. Okay, so if key of left, if A's key is less than B, then merge A's right with B. Okay, and else, okay, so in this case, A has the minimum key, B has the minimum key, merge A with a right of B. All right, is that okay so far? Could not prove termination of this recursive call. Okay, so we decreased A. Why is that one the problem? That's the one that should be fine. Hmm. Right, so we decreased one of the arguments, which should be sufficient. But F star's ordering doesn't think so. Meaning in either we've decreased. Okay, so let's just. So what I think is happening is we're decreasing. We're either leaving A the same and decreasing B, or we're decreasing A and leaving B the same. So that tuple should decrease. Okay, time to break out the assertions. I think I am asserting that okay. Hmm. Right, because I could see if it was getting confused about this. Yeah, because that might be greater in the partial order. Huh. Um. Okay. I should put these assertions above. Um. Hmm. Let me look at the section on the tutorial. Chrome, behave. Well-founded partial order. So yeah, all the arguments should be all the arguments. So for the inductive type, all the arguments should be less than the type in the partial order. I wonder if this is fallout from using -1. Okay, let's try that. Oops. Wow. All right, let's try. What is that? Is that syntactic sugar for something? Alright, I guess I have to restart Chrome. It wants to update anyway. Okay, I just got the syntax wrong on the synthetic tuple. I guess that's a tuple. All right. I think the implicit arguments were screwing up at doing that automatically, so we just had to tell it ignore NPL-A and NPL-B is effectively what we did. But all right. Okay, so we recursively merge, and it gives us a NPL value for that new tree. So we can only use that as our right tree if it's obeys the constraint that right has to be less than or equal to left. So if let new NPL equals uh, the first element of that dependent tree. All right, so if the new NPL is less than or equal to our left NPL, then we're good. Otherwise, we have to swap it. So we return the dependent tuple that's 1 plus min of new NPL okay. And our node has node NPL of A. All right. New left equals node dot. Okay. We're just going to give names to everything. This is both. So right equals d second of new tree. Okay. So if NPL right is less than or equal to NPL left, then they're in the right order to maintain the constraint. So just use them as is. So NPL left, NPL right. So it's going to be the node with NPL left, new left. We need the key and value. So that is key of A. We picked A. And it's the value from A. And then we have NPL right, new right. All right. Otherwise, we gotta swap the trees around. We gotta close the bracket first. Okay, so NPL right and new right. All right, let's see if that type checks. Oh, I wrote min like it was a Python function rather than like it was a F star function. Wow. Okay. So now we gotta do it over for B. It sure would be nice if we could encapsulate all this instead of copying and pasting it. But I'm not that clever. All right, so we're gonna take the left from B. I'm gonna merge the right of B with A. So in fact, we're gonna do it this way. There we go. And then this is all the same. All right, if there's exactly, oh no, it's not exactly the same. We really should find a way to combine those. But all right. So then inserting oops. Inserting. Okay, so we need to take the type, the NPL of the root itself, key and a value. So we're going to I think we're going to have to use the dependent type again. Yeah, I wish that was predictable from our inputs, but I don't think it is. At least not without calling a function that's at least as complex as the whole merge. Okay, so we're going to merge heaps. And heap 1 will be our existing root, and the other one will be a singleton. Okay. And then pop. Oops, I wish we should have kept our pop minimum. All right. I'm actually. It's hard to make a dependent for tuple, so I'm just going to do a type here. Okay, so we've got a key that's a natural number, value that's a v, a NPL, and new root that's a heap node of the appropriate type. Okay, what am I doing wrong here? That type doesn't have equality. All right, I feel like there's a better way to do that, but okay, so this has to be a value that is at least 0 in order to pop. So root, and that returns a pop result of type V. So that is going to be okay. So if we got a node, just to extract all the values back out, got a node NPL left, left, NPL right. Oops. Key value, NPL right, right. So we return min value using the key and the value. And okay, no, we need to new tree equals merge heaps. So we're going to merge the left and the right. And then the NPL is the first element of the new tree, and the root is d second. All right. Not a lot of type problems. Lots of other problems, like the fact it took me 2 hours and 8 minutes to get this far, but we can keep going a little bit yet. All right, so the reason we were doing all this is so we could implement Dijkstra's algorithm. So now we have a priority queue. I'm going to be able to make this a total function. I think the answer is not easily. So we're given a matrix given a width, a height, a matrix of, how did we parse it? Do we parse this as natural numbers or is we parse this natural numbers? Yeah. Matrix N of width and height. And we're going to return a natural number. Okay. So run Dijkstra's algorithm. We're going to have a priority queue. Okay, so we're going to have the weights, which is our input matrix. We need the width and the height as arguments. Okay, we're going to have a the minimum distance known so far, and that has to start out at plus infinity. So let's create a type that does that. So it's either infinity or finite that. Okay, good. So we're going to have a distances, so that's the matrix with of distances a size, width, and height. And we're going to need a way to update that. We're either going to need to make that references so we can do imperative updates. We're going to need to write a function that returns a matrix with an element updated, which we can do with split 3 now that we know the secret of how to do that. So sure, let's try to write this without stateful operations. So then we have an argument which is the okay, so we've got the priority queue NPL, which is an int1. It could be -1 when the queue gets empty. And then we've got the okay, and the values we're going to put in the heap node are XY pairs. So Y is a natural number, X is a natural number less than the width, and Y is a natural number less than the height. We need times. Okay. All right, and that gives a complete distances matrix. It's not going to be total though. I think it's going to have to be divergent. Because so a lot of things are going to well, it's not inconceivable we could prove it's total because the distances matrix is going to get smaller each time. Right? We'll go from infinity to a finite value. We'll decrease the finite value. Can we guarantee that at least one value decreases each time? I'm not sure of that. All right, we'll prove it with the simpler assumption. All right. Dijkstra's of M, and we need an all infinity matrix, and we need a empty heap. Will that work? Not sure. We actually need something to get started. So the empty, it's not an empty heap, it's a singleton heap. And our pair is, our key is 0 and our value is 0, 0. So that's the upper left-hand corner. That's the distance to 0 because we start there. Right. So width minus height minus 1. Why is y not found? Oh, I used the wrong parentheses. Okay, heap node. Okay, this has to be. Okay, that value. Okay, yeah, I got the name wrong. It's just DV. Okay. Okay, this says 0. Computer type distance. Oh, okay, so we're making progress. So let's do the easy bit. Oops. I don't know, maybe if we'd written the slow part, it would have just run a while and we'd be done by now. Okay. So I think we need our integer range functions to do this in the smart way. Otherwise, we can iterate twice, but that's something of a pain. Did we use that here? We did. All right. So once again, we learned we should have put all this in a helper library, but did not. All right, so this. Okay, we can just we should go further back. All right. Okay, so row y, the index of the row is y, and that's going to return a vector of distance of w. Let me look at that up in the 2020. What day was that? Okay. Oh, we don't need that. We only need the return value. Okay. Oops, what happened there? All right. Row returns a matrix, a vector of distance objects. Row. Okay. Okay, we're going to say here is if x equals 0 and y equals 0, then finite 0, else infinite, infinity. Oh, we don't need that. Okay, so that iterates over the row numbers and the column numbers and builds up the whole matrix. All right, so there's start matrix. I don't know if we could have left those both as implicit, but all right, that type check. So all you have to do is actually do Dijkstra's algorithm a step at a time. Okay. So if the heap is empty, then just return all our distances. Okay. So otherwise we want to pop min of our priority. I'm going to call this priority queue. Key value NPL new root. All right, so here's where we depart from strict Dijkstra's is that particular value might be in the queue multiple times instead of just once. So we gotta check for that. So if let's see, we said it's x comma y, so second value, first value. Maybe we should put that in order, but that's okay. The type checking will ensure we keep them in the right order. All right, match. All right. I don't think this should happen, but if it does, Can we write this a better way? Okay. If it's infinity or it's finite and greater than key. The keys are our distances. Let's see, for Dijkstra's, should we update right away? I'm getting tired. Yeah, okay. This is fine. We don't even need to. We don't really need to do anything with it here. We need to update our neighbors. Okay. Oops. All right. This is so much easier in imperative language. Maybe I should have done that. All right. All right, let new distances equals update neighbors. All right, it should be the case that for everything in the queue, for everything in the queue, we've already set a distance. And that seems like a very hard property to show. That's what we need for correctness. So I'm just going to write it as an assumption. So I'm going to assume that the value okay. I'm going to assume it's finite. So we're going to update our neighbors with the new value. Okay, so we're going to have to give the weights, the distances, the index of the point we're updating and its neighbors, and get back a new distance matrix. And then we're going to want to put all those neighbors on the priority queue with their new distances. So let new queue equals cert neighbors distances. We want to insert the new distances. Okay. This is a recursive function. Okay, so same weights, new distances. All right, so let's write the types for those two utility functions we just defined. So update neighbors. Weights. Distances. Y. X. And the distance to xy, which is a natural number. Okay, and that is a total function that returns a new distance matrix. Okay, and so I guess that's not helpful. We need to insert. I guess it was helpful. So we don't need the weights, but we got distances. Okay, this is where we're going to get ourselves into trouble. If things that can appear on the queue multiple times, we don't want to insert their neighbors multiple times. So we could have three values in the distance matrix, one for infinite, one for finite, and one for it's finished. Don't visit again. We could insert things into the queue only when they change, and they'll only change a finite number of times. Yeah, okay, so we're gonna only insert them. We need to do both of these at once. I don't like that. All right, let's all right, we'll only insert if they're not finished, but now this assumption is bad. Okay. Let's finish node distances. It doesn't feel like the right thing, but probably because it's getting late. I'm gonna have to shut down the stream in a couple minutes here, probably before we get finished. My laptop keeps bending backwards. I think I'm doing that on him. All right. What is the right thing to do here? I think this is it. All right. Okay. Infinite. Let's just assume again v. All right. If we already finished, then we don't need to do anything. So we leave the distances alone. Yeah, that insert neighbors is a problem. All right, so All right, so if we already finished the value that's the minimum in the priority queue, we already finished it when it had a lower value. We don't need to do anything. We're just popping it off the queue and going on with life. All right, so if it's finite n, all right, let me just fix this. Y equals second value. Okay, we finished the node. We marked the node finished. We update neighbors. Y, X, and the value of n we got. We insert our neighbors, need distances, Y, X, and the new root, and then, okay. All right. That looks like Dijkstra's algorithm. And we've got 3 utility functions to write. So update neighbors, finish node. Okay. All right, so this gives us a new priority queue, and we have to use the dependent pair type. How we got there. All right, so if we write all those, problem. It's not infinite, it's infinity. Distances. Okay, we needed interesting. Why is it having trouble with second? That should be a gimme. Okay, what if we specify the type for it there? Parse error. Oh, yeah, it doesn't work. All right. that type checked. So it's been about 3 hours. I think my ability to actually write these is going downhill. So I'm gonna call it a night. We didn't even manage to get 1 star tonight, but we wrote a lot of code. It's not a good thing because we're not real sure that all this works. Although the fact that this merged type checks does give us some confidence, but all right, yeah, I'm gonna call it a night. Thanks for staying up with me. Yeah, the things to do yet are, write these functions that update single values of the matrix. So we need a function that does that on our matrix type, which we haven't written before. So we're going to split and then replace a value and merge it together and merge it together. So we're going to have to use the lemmas that tell us that that results in the same size. And we're going to have to use our insert method 4 times here. And we're going to have come up with some nice way of iterating over the neighbors. So maybe we'll copy the code, from a previous day that does that. So, like I said, I'm calling it a night. We did not manage to solve part 1, and I'm kind of worried about what part 2 might have. So, all right, good night.